What is the gravitational pull between the two? Well, this is a plug and chug exercise, so let's plug and chug. The force due to gravity is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared, times 500 kilograms, times 2,000 kilograms, divided by the distance between them, 3 meters squared. And what do we get? Now, if you don't have your calculator here today to work through this, please make sure that you know how to do it when you get home and access to your calculator. Please make sure you know how to do this. Way too many students mess up when typing this into their calculator. Rough answer here.
Yes.
Okay. Units? What are the units? I hope so, because we're finding force there. All right. Questions up to here, because I'm about to bring direction into it, because we are dealing with a vector.
What happened with the variables, next to the 10 to the power?
Oh, those are the units? Those are units,
Oh, okay.
not variables. Yeah, the kilograms squared would cancel out with those 2 kilograms there, and the meter squared cancels out with that meter squared. And so we'll just left with newtons.
Okay, thank you.
Yep. Other questions? All right, direction. What is the direction of the gravitational force acting on the 500 kilogram mass? Again, the question is, well, in essence, is that gravitational force pulling them together or pushing them apart or making it go sideways?
Should be pulling them together.
I would hope so. So it's being forced to the right. What about the force on the 2,000 kilogram mass? I hope so. Otherwise, Newton's third law is complete bunk. That would sort of destroy a lot of what we do here. They're being pulled together. So I need to somehow indicate the direction. Well, the direction of this mass is relative to this one. It's going to be pulled towards it no matter what. And so formally, the force due to gravity of the force on 1 from 2. So this is the gravitational force on mass 1 from mass 2. got my magnitude right there, big G, mass 1, mass 2 over the distance between them squared. But it's, mass 1 will always be pulled towards mass 2, if those are the only two objects there. And so it's relative to mass 2, and then the minus sign indicates it's towards. Again, the radial unit vector means it's away. The r sub 2, this is a vector that's pointing away from mass 2. The minus sign means the opposite direction, so it's being pulled towards mass 2. This is the formal way to write the force between these two masses. And this leads to some moments. I got a number line right here, I got 0 here, I got -3 meters here, I got 3 meters here. Let's put 2,000 kilogram mass right there in the middle. I'm gonna put a 500 kilogram mass right there, a 500 kilogram mass right there. I want you to think a moment before anyone blurts anything out. What is the net force on the 2,000 kilogram mass? What is the total force, net force, acting on the middle mass? And we just went through the complicated, you don't have to do much math here, because we did the math of the force between these two objects already, and therefore the force between these two objects. So, the three most common answers that I see are 0 newtons, 7.4 times 10 to the -6 newtons, or 14.8 times 10 to the -6 newtons. Those are basically the three most common answers. Only one is correct. Which is it? What is the total force? Now it's time to share.
I would say the 14.8 times 10 to the -6.
Okay, anyone else?
I'd say 0, because they're pulling in opposite directions.
Good. Anyone else? Anyone want to go for the middle one? Well, those are the two most common answers that I get. All right, Kenny, what's your argument for the 14.8?
Because the two objects are still going to be, well, the 2,000 kilograms are going to pull on both of the objects at the same time, since the 2,000 is in between the 500s.
All right, so this will be pulled that way, and that will be pulled this way, and this will be pulled that way, and that will be pulled that way.
Right.
Okay? So each of these forces should be of equal magnitude, so this is 7.4 micronewtons, 7.4 micronewtons, 7.4 micronewtons, 7.4 micronewtons. The two 500s are also exerting a force on each other. I'm not worried about that right now. Direction matters. Think about the 200 to 2,000 kilogram. I got 7.4 going to the left and 7.4 going to the right. They would cancel because they're opposite directions. The answer is indeed 0. 0 newtons, not on. And this is especially true in 152, but you gotta pay attention. Think through the directions or play strict adherence to the directions. So if this is my mass 1, mass 2, and mass 3, then the force acting on mass 2 will be the force acting on mass 2 from 1 plus the force acting on mass 2 from 3. Basic, my total force is just the sum of the small forces. This is going to be negative 7.6 micronewtons R1 hat plus negative 7.6 micronewtons R3 hat. just plugging straight into this formula right here, where the subscript for the unit vector there is just whatever the second number is. The reason why you can't add them straight up doing it this way is the fact that R1 hat and R3 hat are in different directions. Where the problem takes place in the middle, R1 hat is going that way and R3 hat is going that way. So if you're doing strict adherence to the math, you need to reconcile it. In the middle here, R1 hat's going this way, R3 hat's going that way. They're in opposite directions. So this technically would be negative 7.6 micronewtons R1 hat plus negative 7.6 micronewtons negative R1 hat. Because at that point they're both unit vectors, so the magnitude's the same, just opposite directions. The negative signs cancel out. And now it's just a negative number plus a positive number. Questions to hear? Because after all, this is in the circular motion problem chapter, so we probably should connect it there. All right, let's take a small little break, stretch legs, whatever you need to do. Preferably don't smoke them if you got them. And we'll reconvene in about 5 minutes and we'll see what food we got. Or I have. Sit here. If anybody would like some carrots?
little planet,
What's that?
yeah.
X.
Okay, thank you.
I was gonna make it Earth, but then I thought, if, it doesn't have to be Earth. We're gonna go through the exact same process that we have for every problem for the past several years. Or weeks, some unit of time. Like time has any meaning for the past year. We have what the heck, let's call it a planet. It could be an asteroid too. We have something that is orbiting the sun at a constant speed. How do we know that there must be some net force acting on it?
So you know what, sir?
How do we know that there has to be a net force acting on planet X as it goes around the sun?
It's going around the sun.
Yeah.
What would it do if it did not have a net force acting on it?
Just keep it going whatever direction.
Yeah. Straight line. So, force diagram. What are all the forces acting on planet X?
No,
We'll get over my glasses at you. We can do better than that. Help Brandon out.
Oh, Brandon didn't say that.
Oh, who said gravity? Amajay, help Amajay out. I'm looking over my glasses at you, sorry to give you the eye.
I can,
Amajay. What's wrong with saying gravity? Somebody help him out. What did he forget?
Force due to gravity?
There we go. So we do have the force due to gravity. That part is, the spirit of what you were saying is correct. Oh, wrong one. It's not weight because we are too far removed here. Once you get to outer space, weight probably is not the best wording. What on normal force?
Not touching anything.
I hope not. Other? Tension? Yeah, I assume there's not some invisible string there that's holding it together. Friction?
No normal force and no friction. Or,
Oh, without normal force, there's no friction. Okay. Yeah. If there's friction, it's got to be rubbing against something. All right. So we have a single force there. What is the direction of the acceleration of planet X?
Right there, it's down towards the center.
Okay. No matter where it is, it's always towards the center. So my acceleration, we'll just take it at this point right here, and we'll just say the acceleration is right there. Oh, there is a force that the planet exerts on the sun of equal magnitude, just opposite direction. I mainly care about this one. I'm not worried about the wobble of the sun. Acceleration done. My coordinate system. What do I set up as my coordinate? Axis. Axis or axes, whatever's appropriate.
there would just be one, in this scenario, down would be positive.
Okay.
to the vote.
We don't have to label it as I or J because it's, ultimately it's, at that moment, it's a one-dimensional problem. Done. Do I need to decompose my one force?
Hope not.
Yeah, I'm not also. Done. Equation of motion. And there's indeed only one equation because I have only one direction to find. What is my equation of motion? You're gonna force me to pick on somebody, aren't you? Mackenzie, what's the equation of motion?
FG equals to
Yep, there we go. And now substitution. I have three things here. For what do I have an independent formula? There's one of them, and
No, never mind, it's good.
well, at least we'll get that one done. M v squared over R. Or technically M times v squared over R.
Gravitational force.
Yeah, that was the formula we just did. So big G times mass of X times mass of the sun over the distance between them squared. Now, I haven't really set up a problem here. All I've done is just basically, this is the same exploration that we would do regardless of what I asked for. We can simplify this sum. S-O-M-E, sum. We can simplify it a little bit. The fact that I have R squared here and I have R over here. So R is just the distance from center to center. That's R. In other words, the orbital radius, 1 astronomical unit. So G, mass of X times mass of sun over, well, that one of those R's cancels out with that one. What mass is this? This is mass of X or mass of the sun? You got a 50-50 shot if you have no idea. When you plug in the F equals ma, what mass is involved here?
The mass of the sun,
Why?
because that's the one exerting the gravitational force,
Then
or the
that-
gravitational pull.
So when you're in free fall, let's say that you jumped off the table onto the ground. When you plug in the F equals ma, you'd have the weight acting on you is equal to mass times acceleration. And so that's m, this is mass of u, so mass of kno times g. And this would be mass of the planet.
Oh, no.
Yeah. It's the mass of whatever is accelerating.
Okay.
So, this would be mass of planet X. So that would actually go away too. That would cancel out with that. So if G times mass of sun over the distance between them is equal to V squared. I'm going to take this one step further, just as we explore it. V is the speed of the Earth. It is not the velocity, because velocity has direction, and I don't care about that right now. What's the formula for speed? What would you need to know in order to know what your speed is? Besides the speedometer.
Distance and time.
Yeah, so what do we do with distance and time to get speed?
we put distance over time.
Okay, so I have distance over time. This thing is traveling in a circle. What is the distance then, for it to go around once?
2 pi. 2 pi squared?
Two pi.
Two pi.
R.
The angle would be 2 pi, but the distance is 2 pi r.
Okay,
So 2 pi times r divided by the time it takes for something to go around once is called the period. So for any repetitive motion, the time for it to happen once is period, and it's symbolized by capital T, is the period. For repetitive motion, T is time to do it once. I'm gonna go for the formality of the language. If this were the Earth, what would be the period?
365 days.
It's interesting, I've had other people go that, immediately to that one instead of just 1 year. But, yeah, 365,
0.25.
closer. And don't forget, every 400 years, we skip leap year. Year 2100 will not have a leap year. Will not be a leap year. All right, so I can now take my v squared since I have another formula for v, and that's 2 pi r over capital T squared. So now I have this gravitational constant times the mass of the sun over r, the distance between planet X and the sun, is equal to 4 pi squared r squared over capital T squared. What I'm going to do is I'm going to get r and t over on one side and everything else over onto the other. In other words, for anything going around the sun, I'm going to get all the constants on one side. G is a constant. Mass of the sun is constant enough. 4 pi squared are constant, so we'll bring those down. Bringing those down. R comes over, and that's going to be equal to r cubed over t squared. What this tells us, if I know the distance from any planet in our solar system to the sun, and I know how long it takes to go around the sun, this relationship of that distance cubed over that time squared is constant for everything in our solar system. Kepler's second law of planetary motion. So here's my, it doesn't quite have the emotion that it did a couple years ago, just because I've done the Kepler rant enough. So sorry about the loss of emotion and the emotional content here, but Kepler spent 40 years of his life coming up with his 3 rules of planetary motion. Number 1, he realized planets travel in an ellipse. So basically, and the sun is at one of the foci. So for an ellipse, what a foci is, if I take 2 points, and then just imagine that I have a chalk or a corkboard here, I take 2 pins and I stick them into the corkboard. I take a string, and I stretch that string out so that the distance from one of those points to where my pin is to the other point is always constant. So if I'm over here, that distance from there to there to there is the same as from there to there. And then I draw around so that that sum of those 2 distances is always the same. That's an ellipse. The foci is one of those 2 points. This is known as a focus, or plural foci, or foci, I guess, if you're more of a purist. That's rule number 1. Rule number 2 is that the distance cubed, the average distance cubed over the period squared for any planet in the solar system is a constant. And rule number 3 is that the equal area and equal time. So if I have my sun right here, and I have the Earth right here, as it goes whipping around the sun, It's exaggerated, the Earth is closer, it's almost a circle. That if, let's say 1 month, the Earth goes from here to here, this is the area swept out by the Earth in terms of the language used. So if that's 1 month there, then when the sun, Earth is closer to the sun, the area of this is the same as the area of that. So it travels faster the closer it is to the sun. Sort of a slingshot effect. It gets closer and goes whipping around, and then it slows down as it gets farther away, and then it speeds up as it gets closer. Third law. 40 years of his life. It can now be derived in an afternoon if you know calculus. So I just pictured, I will say that I'm glad Kepler was dead by the time Newton came along. So just imagine you spend 35 years of your life so far, you don't know it, but 5 more years to go. You're at a bar and Isaac Newton's there. We'll just say he's not Sir yet. And they get to talking about what you're doing. And Kepler goes first. He says, well, I'm looking at the planets and how they move around, and I'm using some really precise data, trying to figure out the rules of planetary motion. I think I almost got 3 of them, but I'm not 100% sure. And Newton goes, oh, got an afternoon, I can show you how to do it. The other science cruelty joke would be the guy who came out with the radius of the Earth, the Egyptian scientist from 2000 BC or whatever, 1000 BC, figured out the radius of the Earth within, I think it was within 5%. And it happened to be, you needed a stick pointing perfectly straight up